So a beam of monochromatic light from a distant galaxy is used in an optics experiment on Earth. Okay. So the beam is incident normally on a double slit. The distance between the slits is 0.3 millimeters. As screen is at a distance d from slits. The diffraction theta is labeled. Okay, everything is fine. A series of bright and dark fringes appears on the screen. Explain how a dark fringe is formed. Okay, so why do we get this one? Now, what is this actually? This is nothing but your IB-DPP9 experiment. Young's double slit experiment. So in an Young's double slit experiment, what exactly happens? The light comes from here, and then there is one beam of light which goes like this here. Another beam of light which goes like this here. It hits it across, and then because of this superposition of these two parts, there is a bright fringe or a dark fringe happens. Okay, this is what is happening. Now you need to expect. Now partially we already expect. Now let us write it down. How do we expect? So this is for how many marks? This is for 3 marks. So you need to put 3 points out. The first point is that superposition of two waves from, not two waves, superposition of waves from each slit at the screen happens for 1 mark. Okay, and then the second mark. If the path difference between these two waves is lambda by 2. Okay, you can either write path difference or you can also write phase difference between these two waves is phi. Then what will happen? Amplitude is your third mark. Amplitudes cancel, and hence destructive interference happens. This leads to dark fringe. Okay, you write so much, but definitely you get a full mark. Next, the wavelength of the beam as observed on the Earth is 633 nanometer. Lambda is given to you. Separation between a dark and a bright fringe on the screen is 4.5. Okay, now calculate. You know, you get a bright fringe here, you get another bright fringe over here. This bright, in between there's a dark fringe. Okay, and therefore the distance between these two is what you call it as a fringe width beta. And if at all, if I consider distance between one dark fringe and a bright fringe, center of bright fringe, center of dark fringe, this distance would be half of beta by 2, right? And this value of beta is given by the formula lambda into capital D divided by small d. The lambda is wavelength, capital D is the distance between the slit and the screen, and small d is the distance between two slits. Okay, now what is he asking? He is asking you to find out the value of d. So therefore I will write d is equal to beta d divided by lambda. Now is the value of d known to us? Let us find out what all has been given to you. So value of lambda is given to us. Lambda is given to us. Distance between a bright and a dark fringe is given, which means what? Beta by 2 is given to you, not beta. Beta by 2 is 4.5 millimeter. Beta should be 9 millimeter. This is given to us. Okay. Beta is given, lambda is given. What about small d? Let us go back to the small d is also given. The distance between two slits. Let us substitute all of them and get that. Very easy problem. So 9 into 10 to the power of minus 3 multiplied 0.3 into 10 power minus 3 divided by lambda. What's the value of lambda? Lambda is 630 nanometer. 630 to the power of minus. Okay. So this is how much do I get? I get 9 multiplied 0.3 divided by 633. Get the answer as 0.0042. 0.0042 multiplied by minus 3 minus 3 minus 6 minus 6 plus 9 would be plus 3. So what is the answer I get here? I get 3 would be 1, 2, 3, 4.2. 4.2. Okay, there is 1, 2, 3, 1, 2, 3. There are 3 significant figures, right? Let me find out what is the third I write 6. Let's see, 4.26. 4.26. That's right. 4.6 meters. Okay. Now let me move on to the next one. The air between the slits and the screen is replaced with water. Take up the entire YDSC, put it inside water. Okay, don't disturb it. The refractive index of water is 1.33. Value of mu is 1. Calculate the wavelength of light in water. How do we do this? Now we know. So what we have done is, this is YDSC and the refraction or refraction have also been combined over. Okay. Now we know C by V is equal to mu. Refractive index equal to velocity of light divided by velocity of light in medium. So this is what is refraction. Now, so as a result of this, now you need to calculate this. We know that this can be written also be as F times lambda air divided by F times lambda medium. I can write like this. Okay. Now this F does not change. F goes away here. So I need this value of lambda. So lambda medium is equal to lambda air divided by, what's the value of lambda air? It's already given to you because it was conducted in the air. Lambda air 633 nanometers. So substitute that value. 633 divided by mu value is 1.33. Okay. Now let us calculate this. What is this lambda? Nanometer. Okay. Let us calculate this value also, which would now be 633 divided by 1.33, which would be 475.9, which is 476. 476 nanometer to answer. Then lastly, state two ways in which 476. State two ways in which the intensity pattern on screen changes. You need to mention, because of this replacing this YDSC experimental kit inside water, what exactly happens to the intensity pattern. So towards it, what can we say? We know that beta is equal to lambda into capital D by small d. See, when you place this entire apparatus inside water, this D and small d does not change, but this lambda is now changing, right? So what's happening to lambda? Let us look at compare the values of it. See here, earlier it was 633, now inside water it is 476, which means what? The value of lambda is decreasing. When the value of lambda is decreasing, then what can happen? First one, the value of beta also decreases. But don't just write beta over here. You should mention distance between the peaks decreases. The first one, you get 1 mark. Secondly, now the entire wave is not only coming inside here, it's coming inside water also. So when it comes to water, what will happen? It's in a different media, right? When it enters into a different media, automatically a lot of scattering will see. Okay, so scattering of light is observed more in water. What do you mean by scattering? First of all, light comes and falls into water, then it gets here and there, it gets scattered over there, and the amount of light that comes and falls onto the screen is very, very less, right? As a result of it, what will happen? Intensity will decrease, right? Okay. So natural phenomena you should look at it. Okay, so do not get confusing. What is that we do? So on. So just look at it as if you are conducting the experiment, and then write the whatever is the phenomenon. Okay. So I think with this we have come to an end to this paper. So tomorrow we will see the next day.